All right, this is Mr. Smith here. We are progressing quite nicely through Algebra 2. You're more than halfway finished. I hope that feels good. On the same note, though, conceptually we are going into more difficult territory. The reason that Chapter 7 is difficult is there are two primary reasons. Number one, we don't do a good job of thinking exponentially. And I'll prove that to you in just a moment. Our minds have a hard time wrapping around the idea of exponential growth. Okay. The second reason is because we introduce an entirely new notation structure. Okay, so you guys are used to writing exponents in one way, and in this chapter we introduce an entirely another way to write them, and it's called logarithms. Okay, and by and far, this is a very difficult concept to wrap your mind around. We have an entirely new way of writing some expressions that you're used to writing one way. We write them another way, and then we do mathematics on that. So that's what makes this chapter hard. But exponential growth is very, very important in sciences, especially biology. In fact, you've probably already seen it. Any of you who have taken any biology have already seen the idea of exponential growth, because cells expand and die in an exponential fashion. Radioactive decay is the way that carbons decay over time, happens exponentially. Viruses spread exponentially. And so understanding this concept is underlying to that and to finance. When you invest money in your savings account that gets 0.75% presently in 2013, that's ING Bank, which is an online bank, 0.75% annually, that compounds, and that is an exponential idea. And we'll look at some finance problems as we proceed through this chapter. Now, here's a list of some of the things that we've seen already. This is a linear equation. We studied those a lot in Algebra 1. This is quadratic. We studied those pretty heavily here. How to graph them, how to solve them. We have our polynomial equations, just a generic polynomial equation. In the last chapter, we saw radical equations, cube root equations, fourth root equations. We worked with rational exponents. So you've come a long way. And in the most part, we can talk about how to graph these. We can talk about how to solve different types of equations. So those are some big steps. The type of equation we're going to work with solving now is an exponential growth equation of the form y equals b to the x, or y equals some number, and the variable now is in the exponent's place. Okay, the variable is now in the exponent's place. Okay. The domain of this graph, the domain of this function is from negative infinity to infinity. Okay, I can plug in any number for x. Okay. And the other piece of this is the range is from 0 to infinity. So as I come up the y-axis, the graph starts here on the other side of 0. And this is a very difficult idea to get a grasp on. But this graph keeps getting smaller and smaller and smaller, but never touches the x-axis. So think about it. The graph gets smaller and smaller and smaller and smaller and smaller, but yet it never touches the x-axis. Okay. So that's why the range here, we talk about the range, is from 0 to infinity, and the 0 is not included. 0 is not included. This graph will never touch 0. And we call this phenomenon, this idea that it's getting closer and closer and closer and closer, we call this line that it gets closer to, in this case the x-axis, we call that an asymptote. An asymptote. It's a funny word. No idea where it comes from. You should look into it. But the idea is that this graph will never touch the x-axis, and so the x-axis is an asymptote. A-S-Y-M-P-T-O-T-E. Asymptote. And we study these a lot more in pre-calculus. They're very important in our understanding of mathematics. Okay, so let me give you an example of some exponential growth. And for those of you who are at home, you're going to have to visualize with me. So I have a standard sheet of paper in front of me. I'd like to do a magic trick with it. I don't know any, but maybe I'll come up with one. But what we're going to do is, standard sheet of paper. It is 0.1 millimeters thick, standard thickness piece of paper. And I'm going to fold it in half, like so. So now the thickness is 0.2 millimeters, right, because I just folded it in half. And I fold it in half again. So now our thickness is 0.4 millimeters, right? And I fold it in half again. And I know that on Mythbusters they've shown that you can do it 11 times. I think they use the steamroller and some other things. So I'm going to ask you to join me in the realm of theoretical, okay, the theoretical realm. So you cannot practically fold a paper 40 times, but I'd like you to imagine if you could, if I folded this piece of paper in half 40 times, how tall would it be? And let me give you a couple values to kind of set your mind thinking. So would it be up to my knees? Okay, so I'm a 5'8" person if you're watching at home and have never met me. 5'8", so up to my knees, up to my waist. Say the ceiling, it's a one-story ceiling, so up to the height of the one-story ceiling. We're in a two-story building, so maybe smaller than the building, or let's just say taller than this two-story building. Okay, so if I fold the paper 40 times, how tall will it be? So you think on that for a moment. If you're at home, you think on it for a moment, and don't cheat. Okay, so let's think about this mathematically. So we're going to be in the units of millimeters. So I'm about to go through the answer. If you want more time, you should pause the video. All right. So our paper was 0.1 millimeters thick. So our unit is millimeters. Okay. And I'm going to double its thickness, so times 2. And I'm going to double its thickness how many times? 40 times. Right? Double the thickness, 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 double the thickness. So 0.1 millimeters, that's our starting width. I'm going to double that 40 times. And this equals that number. Now, remember though, that's in millimeters. How do I convert that to meters? Nix off 3 zeros. So now we're in meters. How do I convert that to kilometers? Nix off another 3 zeros. And I'm left with that number. 110 kilometers. That is roughly somewhere between a third to a fourth of the distance to the moon. This is what I mean when I say our minds don't grasp the idea of compounding very well. We're not generally exposed to this phenomenon, and thus we struggle to wrap our minds around the fact that when I fold a piece of paper 40 times in half, I've just made that paper's thickness a fourth of the distance to the moon. So distance to the moon is 350,000 kilometers to 400,000 kilometers. It generally varies in between that range. Okay. All right. So we're going to start off this chapter by talking about graphing. Talk about graphing. All of our knowledge of graphing still applies here. We can use an XY table. In fact, we're going to. Also, our understanding of transformations is going to come into play. So here we go. XY table. I pick a few x values. So let's pick an x value of 0. So if I plug in 0, I get 6 to the 0th power, which is 6 to the 0th power is just 1. 1 times a fourth is a fourth. Okay, 6 to the first power is 6 times 1/4 is 3/2. 6 squared is 36 times 1/4 is 9. 6 cubed is 216 times 1/4 is 54. So on the right-hand side, you can see this starts at 0 1/4, something like that. 1 3.5, and 2 9. We're already off the chart, maybe up here. And 354 certainly is off my graph. If we come to the negatives, -1. What's 6 to the negative first power? 6 to the negative first power is 1/6. 1/6 times 1/4 is 1/24. 6 to the negative second power is 1/36 times 1/4 is 1 over 144. So you can see this is getting closer to 0, but it will never reach there. And that's what the graph looks like. The graphing calculator will graph these, but you should still have a fundamental understanding of how to do it by hand. Of course, I will let my students use calculators. But I'd like you to see what's going on. It also means if you look at the graph at the wrong zoom, or the wrong window, you may see nothing, because this graph takes off so quickly. So if I get too far over here, I may not see the graph. And if I get too far over here, I won't see this line because it'll practically be on the x-axis. Okay. And this is the idea of exponential growth. It grows super duper super fast this way, and also it gets super duper close to the x-axis. Okay, as close as you can possibly imagine, and then closer still, and then closer still, but yet it never reaches the x-axis. This is an asymptote. All right, so the x-axis here is the asymptote. The domain of this function, all real numbers. The range of this function is from 0 to infinity, but 0 is not included here. 0 is not included, so it should be a rounded parenthesis, not a square one. Okay, let's take a look at one more graph and we'll be done for the day. The lesson will continue tomorrow. So here we're going to graph this. We're going to graph this piece. And before I do, I want to talk through transformations. Right? What do you think this -2 will do at the end? Right, we've seen this over and over again. A number at the very end creates a vertical shift down 2 units. It's exactly the same. This creates a vertical shift down 2 units. What about this -2? It's a little unfortunate that it's also -2. What do you think that will do? Well, we have 4 transformations. We've already nixed vertical shift. It's not going to do a reflection, so I'll nix that. So you only have 2 options. It's either the horizontal piece or it's a stretch. And in this case, this is the horizontal shift. It's going to shift this graph 2 units to the right. This is 2 up front. That's going to create a vertical stretch, a stretching factor somehow. How is this thing going to stretch? No idea, but it's going to stretch. Okay, so look at our transformations. We have a vertical shift down 2, horizontal shift to the right 2, and a stretch factor by 2. Okay, so let's plug in an x value of 2. See what we get. So 3 to the 2 minus 2, which is just 3 to the 0th, is 1. 1 times 2 is 2. 2 minus 2 is 0. I plug in 3, I get 3 to the 3 minus 2 power, which is just 1. So 3 to the first power is 3 times 2 is 6 minus 2, 4. When I plug in 4, I get 3 squared, which is 9 times 2 is 18, minus 2 is 16. Okay, so at this point, I'm already at 416. I'm way off the graph, so I'm not going to keep going. Let's plug in an x value of, let's say, 1. So this becomes 3 to the negative first power, which is 1/3, times 2 is 2/3, minus 2 is negative 1 and 1/3. If I plug in 0, I get 3 to the negative second, which is 1/9. 2 times 1/9 is 2/9. minus 2 is negative 1 and 7/9. Okay? And so let's take a look at the graph here. So I get 2, 0, I get 3, 4, I get 4, 16. Okay, so that's up there. Here I get 1, negative 1 and a third. So that's there. Here I get 0, negative 1 and 7/9. And what you can see is a graph that looks like this. There we are. There we are. Okay, let's talk about domain and range. Domain here is negative infinity to infinity. Range. So this graph has been shifted down 2 units. So range is from negative 2 to infinity. And notice again, I'm using a rounded bracket, not a square bracket, because this graph will never get a y value of negative 2. There's an asymptote here at the line y equals negative 2. Okay. And this concludes part 1 of section 7.1. Thanks for your attention.